Hi folks, this is lecture 9 of the mechanical vibrations course, and this is what we have on the agenda today. Let me switch. So we're going to be talking about force transmissibility for a stationary base. Okay, in other words, suppose that you have uh, an object, a mass sitting on a spring and a damper, and there is a harmonic load acting on the damper as a single degree of freedom system. A harmonic force acting on the mass, and the mass moves up and down. Now, some of the force is going to be transmitted into the base. So that is item number 1, where the base is actually not moving. It's a ground, for example. Then we're going to discuss the same topic, but when the base is moving. Okay, in that case, there is no direct force applied on the mass, but the motion of the base causes the mass to move, and obviously the stretching and the compression of the spring and damper and things like that will create a force, which some of it is going to get transmitted to the passenger, for example, or to the mass, not the passenger necessarily. Now, first we discussed the displacement transmissibility, and then we're going to do the same thing for force, which is item number 3. And finally, we're going to start the concept of rotating on balance, but we won't be able to finish it. Therefore, there is the lecture 10 is going to be the continuation of that rotating on balance. Okay. So let's go to our first topic, which is force transmissibility to a stationary base. Here's the ground, and suppose this mass was sitting directly on the ground without being supported by a spring and a damper. If that is the case, and if there is a force acting on the mass, but the mass sits directly on the ground, the entire force, whatever it happens to be, is going to get transmitted to the ground. That should be obvious. But let us now suppose that the mass is supported by a spring and a damper, as you see here. And the force up there is a harmonic force. Okay? If that is the case, we actually solved this problem. We solved the problem of a single degree of freedom system under harmonic loading, and we came with what you see over here. This was the solution from last week. At the end of the day, if you give me the driving frequency omega of this oscillating force, I have to give you big X and the phase angle theta. Now, there is a transient solution involved too, but that transient solution will die after a long time, and therefore the steady state response, which is over here, which we call particular solution, the solution that hangs around is going to be given by that expression. Now, essentially what I'm saying is that the solution to the mother of all equation, which is down here, is the thing above it. This is the steady state solution. At the end of the day, where the transient solution dies, this is going to be the steady state solution to that equation. Now, keep in mind that the force in the spring and in the damper comes from the fact that this mass is moving, xp. So the displacement of the mass times k is going to give you the force in the resisting force due to the spring, and the damping constant c times velocity, which is x dot p or x dot, is going to give you the resisting force due to the damper. So we know x is right up here. You take this thing and stick it in that equation, and you get the expression for the transmitted force as a function of time. Okay? And there we are. So here is your kx. There is your kx. There is your cx dot. The reason we get a minus sign because you're differentiating cosine here. We get a minus sign. And of course, there's going to be an omega in the front. And there we are. This is it. This is how the force is going to get transmitted through the spring and the damper to the ground. This is the transmitted force. Now, I mean, obviously we know everything about it. But one thing you can see that there is a cosine here, right? There is a cosine here, and there's a sine here, and they have the same angle right there. Same angle, omega t minus theta, omega t minus theta. If that is the case, you can actually combine these into a single, either a sine or a cosine involving omega t minus theta, but the amplitude of it is going to be square root of kx squared plus c omega x squared, which is right here. So this you can do because these angles are the same. And what we're saying is that, look, the transmitted force is also harmonic of the argument omega t minus theta, or of frequency omega t and a phase angle theta, and this is the amplitude of it. And there's nothing wrong with it. You can just leave it the way it is. However, we know what x is from last week. Big X. Remember, it was F naught over K times an amplification factor. So I can take this X and replace it with what it is. Here is the value of big X from last week. And then, of course, times square root of k squared plus c squared omega squared. Now, there is a little massaging we're going to do here, because remember how nice this thing was? There was R and zeta only. But here we have C, K, and omega. So we're going to massage this a little bit. First of all, I take the k squared out of the radical. Out of this radical, I take the k squared out, and there's the square root of it, so it becomes k square root of this fellow. Now, first of all, this k cancels that k. And then here, just literally write down what this thing reduces to, okay? Literally write it down. In other words, for example, remember, omega n is the square root of k over m. So, for example, k squared is equal to m omega n squared. Just write it down. You get that. The moral of the story is that we got the transmitted force in terms of this term, that term, of course, once you take its square root, and then 1. Cleaned up version, next page, right there. So the transmitted force to the fixed ground is that expression. You give me the amplitude of the force acting on that mass. You give me the zeta, the damping ratio, the driving frequency. I have omega n, I have r. I have everything on the right-hand side. So the magnitude of the force transmitted to the ground is right here. Maximum force transmitted to ground is right here. Now, the ratio of this Ft over F naught is called force transmissibility. And it's just a matter of dividing both sides by F naught, and you get there. Ft over F naught equal to this. This is called force transmissibility. Now, force transmissibility in the vibrations literature, they also refer to it as 1 minus base isolation. So if you see the word force transmissibility, that's what this thing is. If you see the word base isolation, it's, what is it? It's 1 minus force transmissibility right here. So force transmissibility is 1 minus base isolation, and or 100% minus percent base isolation. Or if you want, you can refer to as base isolation as 100% minus percentage force transmissibility. All I'm saying is that, look, either you're talking about force transmissibility or base isolation. And there's the definition of base isolation, which is simply 1 minus force transmissibility. Okay, this is written for you in multiple places. That is exactly the same as that. Just a reminder. Okay, so let's do a problem. Now, first of all, we know that if you have a mass not supported, sitting on the ground, and the load is applied to it, the entire force is transmitted to the ground. We know that. But we just learned that if we have a mass and a spring there, a spring and a damper there, not all the force that you put up there is transmitted to the ground. Okay? Suppose that this machine is being acted on, this machine or this mass is being acted on by a harmonic load, which could be coming from a machine which sits on top of that with a mass imbalance. Okay? So suppose that the magnitude of this force is F naught, big F naught, sine omega t. In other words, harmonic with the driving frequency omega. Okay. What we want to do is to find the value of K and C, the value of K and C. We're going to design an isolation system, K and C, such that these objectives are met. And what are the objectives? There are two things to be met. When the operating frequency, the driving frequency is 4 hertz, the system should be 40% isolated. And what does that mean? It means 60% of the force goes to the ground. 40% isolation, another way of saying it, is 60% of the force of this magnitude F naught goes to the ground. Not the whole thing, 60% of it, or 40% isolation. And when this is at resonance, in other words, when this driving frequency matches the natural frequency, I don't want the dynamic force transmitted. In other words, I don't want Ft to be bigger than 2F naught. Okay, remember, the transmitted force harmonically oscillate, and we call that thing Ft. Okay, the amplitude of that Ft, which means remember the absolute value of F transmitted, amplitude of that, we don't want it to be bigger than 2F naught. 2F naught. So find K and C such that when omega is 4 hertz, driving frequency is 4 hertz, the force transmitted is 60%. Okay, transmissibility is 60%. Okay, and at resonance, the magnitude of Ft to be equal to F naught or less than 2F naught. Less than 2F naught. That's right. Okay, so let's write down one more time what we said. We are given the isolation. There we are. We are given, you're told that percent oscillation is 40%. So immediately we find Ft over F naught, okay, or transmissibility. So the transmissibility by definition, which is Ft over F naught, is 60%. There we are, 60% or 0.6. That's one thing we want. And then when at resonance, omega equal to omega n, or r equal to 1, we want this ratio to be 2. Just keep that in mind. So let's go here. At r equal to 1, at resonance, Ft over F naught to be 2. Okay. So let us go in here and plug in what we know. Ft over F naught, it has this expression. Okay. It has this expression. And we want this thing to be 2. We know the value of r. Value of r is 1. You just plug it in and you get your zeta. So this condition at the resonance, we want the transmissibility Ft over F naught to be 2, translates into the value of C, zeta. Okay. Now, the second condition, let me remind you what the expression for Ft over F naught was. But keep in mind that The reason it looks like that is that it at resonance, in other words, when R is equal to 1. When R is equal to 1, this is the expression we get. This is not in general true. This is only at resonance. For an arbitrary R, the expression is right here, force transmissibility. Okay. Now, there's another piece of information we are given that when omega is 4 hertz, when omega is 4 hertz, we want this thing to be 60% or 0.6. In other words, the big F of t to be 0.6 of the applied harmonic load, the amplitude of the applied harmonic load. So, do we know R? The answer is yes, we do, because R is omega n. You were told what omega is. Omega is, okay? Uh, the thing that we can calculate out of that, the only unknown that we have here, see, the only unknown that we have here is R, okay? Because we've just found zeta. You plug in R, uh, uh, you plug in zeta, zeta is 0.289. It's an algebraic equation, so by hooks or by crooks, you have to solve for R, okay? Look, this condition at resonance, we want Ft to be at most 2F naught. We'll tell you what zeta is. At resonance, when R is equal to 1. In general, this is the expression for Ft over F naught. We are told the second design condition is that this ratio to be 0.6. In other words, at the driving frequency of omega equal to 4 hertz, we want the Ft to be this ratio to be 0.6. In other words, only 0.6% of the amplitude of the force to become the dynamic force transmitted to the ground. The only unknown in this expression, because we just found zeta, is R. Calculate R, you get that, but now R is omega over omega n, right? We know what omega is, 4 hertz. So for omega, write down 2 pi times 4, because this has to be radian per second, okay? Omega generally is radians per second. So 4 hertz is really not omega. It's this frequency which people usually denote it by little f. But anyway, there it is. We have omega. This omega is 4 times 2 pi. We have m. M was given to us by the problem. We just calculated R, and that'll give us the design value of K. There we are. So we just designed a system that, an isolation system, which meets the criteria that was given to us. We calculated the K, and we calculated the damping coefficient. Okay, problem solved. Okay, let's move on. Now this is going to be, you can view it as a new concept, new topic, where there's a mass spring damper system involved here, but there is no force that's directly applied on the mass. In other words, I don't have a, let's say, a unbalanced machine sitting up there which is running because of its unbalance, it creates the force. There is no direct force applied on this mass. However, the base of it, the base is moving. The ground, here's the ground. Think about this thing as the ground is moving. Generally speaking, ground does not move. But this is why we don't call this thing a ground. We say the base of this is moving. This base going up and down, you can view this thing, for example, as a suspension of a car, okay, going over a bumpy road, okay? The base is moving. The motion of that base creates a compression or tension of the spring and the damper, and these two, the spring and the damper, indirectly, because of the motion of the base, puts a force on the mass. Okay? All right. That's what we mean by base motion. Okay, so mass is attached to a spring and a damper, and the spring and the damper are attached to another, let's say, a base, and it's the base that's moving, and that causes the mass to oscillate. I have to talk about this little x of t in a minute. Okay, first of all, when you talk about the motion of the base, it is from, again, some ground. Okay, no problem. So from some reference point. So the reference point is, it could be the ground, and we're talking about the motion of the base from the ground. But let me put it this way. Let's consider this system. Okay, so when it comes to measuring x, remember, x can be measured from when this base is stationary. Think about it like this. When the base is stationary, when the base is not moving, just literally hang on to it, okay? Obviously, this mass is going to settle down to a location. That location we call the equilibrium position. Now, you can measure x from that equilibrium position, and that's what we have been doing in the past. Or you can measure x from some arbitrary fixed reference. Maybe the ground is down. Maybe the ground is down here. This is you fix the base. You fixed it, did not let it move. This settled down. Okay? So when it comes to measuring the displacement of m, you can measure it from that equilibrium position where it's settled, or from some, who knows, an arbitrary reference point down here. It could be the ground, for example, but that's not what we're doing. We are measuring it from a fixed position, and this fixed position is the equilibrium position of the mass when this base was stay put. Okay, that's why when you write the equation of motion, we can write sum of all the forces equal to mass times acceleration. And the acceleration, we can say x double dot, because x is measured from some fixed inertial reference point, equilibrium position. Okay, so what happens? The mass is moving by the amount x of t in general, up or down, we don't know, we write up, okay? And the resisting forces are coming from the spring and the damper. And how do we know what they are? The resisting force in the spring is the stiffness of the spring times the amount of the stretching or compression, which is x minus y, because the y is moving too. The base is moving too. Not only x is moving, mass is moving, but the base is moving. So the stretching or the compression of the spring is actually x minus y. And for the damper, it is the velocity of relative velocity, which is x dot minus y dot. Okay? So negative k x minus y, negative c x dot minus y dot equal to mass times acceleration, which is right there. So we're writing the equation of motion for this block, and look at it, mx double dot equal to sum of all the forces, which is negative of that and negative of that. We bring it all up to the left-hand side, and we get the mother of all equations as it is now. Now, remember, we know what our y is, and we know what y dot is, because we know the base motion. Otherwise, we can't solve the problem. So let's, for a minute, assume that the base motion is actually harmonic. Like the example that I gave you for in the previous, the bumpy road or sinusoidal profile, etc. So it has an amplitude. That harmonic base motion has an amplitude, base amplitude, and a frequency omega b, because it's a sine curve. Okay, we're assuming it's harmonic. It looks like that. Now, This is what we refer to as the driving frequency, okay? Because it's driving the base, okay? Driving the base. All right. And this big Y is the amplitude of the motion of the base. Remember, what I'm saying is that here's the base. The base moves up and down somehow, okay? Somehow, for a given amplitude, big Y, at the frequency omega b, okay? So we take that fellow, we stick it in there, and clean it up right there. Now keep in mind that where the cy dot goes to the other side, ky goes to the other side, ky is right here, right there. This is ky. And cy dot, you differentiate sine, you get omega b cosine big Y there. This comes from the damper. This comes from the spring. Do we know that? Yes, because we know omega b, we know big Y. Omega b big Y. So do I know the right-hand side? The answer is yes. The answer is yes. It's some of these two, but there's another way of looking at it, and you may prefer that. I don't know. These angles are the same, right? These angles are the same. So you can say that the right-hand side is either cosine omega t or sine omega t, okay? With a phase angle, and the magnitude of that sinusoidal motion is cy omega b squared plus ky squared. But I'm not going to look at it like that, or at least because I'm assuming that you're using the designated book textbook, which is Inman's book. Uh, Inman does not look at this thing as you know what? Let's replace the right hand side with a sine omega bt or a cosine omega bt with an amplitude in the front and a phase angle. He's not doing it like that. Okay, but we have seen things like this. For example, if this right hand side, if this was only the right hand side, we have solved that problem. We have already done it last week. Mother of all equation. Ignore that first term. Right-hand side is a constant times sine. Or ignore this equation, constant right here, including the omega b times cosine. We have done these problems. So essentially, we're going to repeat that, but I want to take a 1 minute digression about this because remember, this equation that I wrote down, the mother of all equation, is in terms of x, right? At the end of the day, mx double dot plus cx dot plus kx equal to the right-hand side, which is those two terms. This is called absolute equation of motion because x is measured from a fixed inertial reference point. It can be the equilibrium position, or it can be some other reference point, such as the ground. This is called absolute equation of motion because when you write Newton's second law, really the acceleration term must be the absolute acceleration or acceleration measured in an inertial frame of reference. Okay? That's what Newton's law says. Now, this is why I put a caution here that this x is measured with respect to a fixed point. And the fixed point may be where the system was stationary, wherever the mass settled down. Okay, be careful. So there it is. Now it is true that I said suppose y is sinusoidal. I plugged it in, differentiated it, and I got that stuff sine omega bt, cosine omega bt on the right. But in general, it's like that. It doesn't have to be sine and cosine. It's right there. Now, we can also write the mother of all equations in terms of this difference. Look at this difference. In other words, the amount of stretching or compression. This is the difference. If I take this and stick it into that equation, already I can see that this is z dot, this is z dot, this is x, this is z, this is z right here. It's defined like that. This is z, there's z dot, and this, of course, is going to be z dot plus y dot, right? X dot x double dot, differentiate this thing twice, x double dot is z double dot plus y double dot, like that. Now notice that I can take y to the right-hand side, looking like this, all right? So some people refer to it as a relative equation of motion because it is written in terms of the relative displacement, the difference of these, the stretching or compression of the spring and the damper, like that. Now, the question becomes, do you like this one better or do you like that one better? Well, probably most of you will say, oh, I like this one better because there's less stuff on the right-hand side, okay? Yeah, and some textbooks and some video tutorials may go that route, which is fine. At the end of the day, you're going to get the same results, but that's not what Inman does, and we're going to go back to our presentation. This was a 1-minute digression. Go that route, or you go this route. This is what Inman does. All right, let's go back. All right, so this is what we have. When y is sinusoidal, harmonic, so the spring force is right here, the damping force is right here. Okay, good. And these two equations I can solve because I can view this thing as two equations. One with the right-hand side being the first term, the other one with the right-hand side being the second term, this term. And these are linear equation. I can do that. This is linear equation. That's why I can break it up like that because superposition holds. So instead of solving this equal to the sum of two terms, I do this equal to first term, solve it, and this equal to second term, solve it. I get x1 and x2, and then add them up to get the final answer. Now, if you patiently do that, as the textbook Inman does, if you patiently do that, or if you take my words, the final answer for xp is going to be like this. There is amplitude in the front, right there. There is an amplitude in the front, right there. And there is a cosine of omega bt, the driving frequency times t, minus these two phases. There is no, don't look at these things, what's the physics, what's the interpretation of that? You can't do that because look, we understand what this is doing, we understand what this is doing, we found them individually, add them up. Elementary math and trigonometry and bookkeeping goes to this. Okay? Theta 1 is tan inverse of that. Remember all those restrictions you have about the phase angle and things like that. 0 and pi. And theta 2 equal to this. Okay? At the end of the day, when you have a base motion, we know how the mass moves. The mass moves like that. The mass moves like that, where you have to calculate theta 1, theta 2 from these equations, and there is the amplitude of the mass motion. Okay? Now, I could have left it like this, but remember, last week we said that why don't we write things in terms of little r, frequency ratio, which means omega b over omega n. Okay? Omega b over omega, because there are driving frequencies omega b here, right? So if you do that and patiently factor out omega n and write things in terms of uh, zeta and r, this is what you're going to get. This is the amplitude of vibration of the base. You know that. You know this why. That tells you what the amplitude of the vibration of the mass is. X in terms of big X in terms of big Y. Some people, and I mean, at least many charts and graphs that you may be seeing, and in fact, you're going to see some of them, is written not as X equal to that, is written as a non-dimensional thing, X over Y equal to the right-hand side. This looks familiar to you with one exception. When we did stuff like this last week, it was not base motion, it was a mass under harmonic load. The magnification factor was, instead of that guy, there was no this second term. It was 2 zeta r squared was not there. But when you have a base motion, it is there. You can't help it. This is called displacement transmissibility. Displacement trans. In other words, what is the amplitude of the mass motion in terms of the amplitude of the base motion? Big Y is for the base. Big X is the amplitude of the mass, vibration of the mass. And remember, this R is omega B over omega N. Now, it can be plotted. It can be plotted like this, right? Believe me, if you plot X over Y, for every value of zeta, you get a curve. And it's very similar to what we had before. But remember, this thing before, there was no base motion. And this thing was big X divided by static deflection, which was F naught over K. We don't have F naught here. We have big Y stuff, okay? It was the same kind of animal, but it was for a different purpose. But the graph looks kind of similar, okay? Now, notice that when R is equal to 1 and there is no damping, in other words, the base motion is at the same frequency of the mass, natural frequency. There's no damping. The mass goes to infinity. But damping brings it down. Okay, damping brings it down. And for example, notice that the graph, there's some characteristic of it that we can pay attention to here. If frequency ratio is less than √2, √2 is right here, where all of these cross each other, right there. So basically, we are on to the left of √2. The amplitude of the mass is going to be bigger the amplitude of the base. So it's magnified. The base motion is magnified. You can see that. It's above 1. See, here's 1. Here's 1. So this is when X and Y are the same. But if you're in this range, to the left of √2, X is bigger than Y. You can see because the ratio is bigger than 1. All right. Now, if you give me a value of R, for example, even here, if you give me the R, we know that the big X is bigger than big Y. We know that because from this range, it's bigger. But notice that damping, the bigger the damping, the smaller that ratio. Okay, so the amplitude of the motion of the base is reduced when the damping amount goes up. You can see that. Let's bring it down. Okay, and in Word, it says for a given value of R and a damping ratio, the value of the damping ratio determines the level of this transmissibility ratio. This is a fancy way of saying that, look, you give me R, how big zeta is, tell you what X over Y is, which obviously we can see it from the graph. Now, if R is bigger than √2, if the frequency ratio is bigger than √2, then this transmissibility is less than 1. You can see that. All below the line transmissibility equal to 1. Okay, and this is true, of course, for all damping values. However, it also tells you that with a higher damping, in fact, it is not as good. Okay, the amplitude of the motion of the mass is less than the amplitude of the motion of the base. That is true because this transmissibility is less than 1. However, as you increase the damping, that x over y becomes closer to 1. Okay? That you may or you may not have expected that. All right, so what's the story here? Car transmission, bumpy road. Are you happy? Probably no. But you put a pillow underneath you. Are you happy? Well, why are you happy? For sure. So essentially what you have done, you have designed a, mass spring, force damper, uh, spring damper system, which puts less force into your body. Okay? So what we really want to know is, yes, it's not how much I move as the car is driving over that bump. That we already know. It comes from the big X over big Y. The question is how much force is transmitted to my body, and that is the topic of the next item. Okay, so over the last few minutes we discussed what the amplitude of the motion of the mass is, in other words, big X, in terms of the amplitude of the motion of the base, big Y. And we got expression involving the displacement transmissibility, which is a fancy way of saying big X over big Y in terms of in terms of a right-hand side, which had in it only R frequency ratio and zeta. Now, what we want to know is how much force is transmitted to the mass. Okay. Now, the only force that's transmitted to the mass is coming from the spring and the damper. And the magnitude of the force from the spring is simply the stiffness of the spring times the amount of stretching or compression, so x minus y, or relative displacement. Okay? And the amount of force that's coming from the damper is the relative velocity, x dot minus y dot times the damping coefficient. Now, the only other force is the inertial force, which is minus mx double dot. But this is not what we're looking for. We're looking at ft like that, or you can get it from this expression also, x double dot, either from here or here. You're going to get the same answers because this force and that force are the only ones that are present, and the force is just mass times acceleration. Okay. Now, let me remind you what xp was, because at the end of the day, we know y. And we know xp because we solved for it. We just go back to the previous 10 minutes. We see the expression for xp. Remember that horrible expression, which had a theta 1 and a theta 2 in it? Remember that? Okay. Now, it was like that. It was right here. If we know xp, I can either plug it in here or there, but it's easier to do it on this right-hand side and get the expression for big F. Okay? Now, notice that this thing is of the form cosine of something right here, and that is what we call the transmitted force. This is the transmitted force, amplitude of the transmitted force. F of t is the transmitted force, but it's sinusoidal. You can see that the thing in front of the sinusoid cosine, the thing in front of this cosine is the magnitude, the maximum force transmitted to the mass. Okay, and that maximum force transmitted to the mass we call it big F of t, or the amplitude of that vibration, or amplitude of that variation of the harmonic force. Okay, so big Ft is the amplitude, is right here, but we're going to clean it up in a minute so that there's only R and zeta. I don't like omega n and omega b, so we're going to do some massaging so that this becomes only, this F of t becomes only in terms of zeta and R. Okay, we'll do that. Okay, but at the end of the day, when you do that massaging, and it's just algebra, in other words, factor out omega n squared out of the top, what do you get? You're going to get 1 plus 2 zeta r squared. So that's where this is coming from. It's just a patience and doing the algebra. You're going to get that the amplitude of the transmitted force Ft is right here. And this ratio of amplitude of the transmitted force divided by some other force, which is just the magnitude or amplitude of the displacement of the base times k. This has unit of force. This has unit of force. This ratio is called transmissibility ratio. And the only thing that happened here when you compare it with the previous displacement transmissibility, remember big X over big Y, we have this R squared sitting there. You already saw something like that in the displacement transmissibility, but there was no R squared in front of it, but now we do. So force transmissibility is that expression, this ratio, and you can plot it, by the way, just like you did the plot of big X over big Y. Now we do big Ft over Ky. Now, it's kind of hard to see what is going on here just by looking at these plots, but let me give you some comments coming from Inman. Well, first of all, the force transmissibility expresses a dimensionless entity. A dimensionless entity refers to a measure of how the displacement of base amplitude, big Y, affects the amplitude of the force transmitted. You can see that. This is the amplitude of the force transmitted. This big Y is the amplitude of the base motion. So we have basically representation of the vertical axis, which is the force transmissibility, in terms of R. Now, first of all, if you looked at the expressions for XP and FT, they both have some garbage times cosine of omega bt minus theta 1 minus theta 2. The term that makes them vary is that cosine term, and the angles are the same. In other words, they're in phase. Now, let me go back a couple of slides, last slide, and I'll come back again, just a second. Right there, you see that? This was, see this? This was cosine omega bt minus theta 1 minus theta 2. That is the force. Where did it come from? It comes from the expression xp equal to big X times cosine of also omega bt minus theta 1 minus theta 2. In other words, the force transmitted and the displacement of the mass are in phase. That's what this is saying. Xp, for displacement of the mass, and the force transmitted are in phase. Okay? Because they both involve that term. And it tells you where to find it if you want. Already showed you Ft, but Xp was in slide 9. Good. Now, these go together. These two go together because the first sentence happens because they both have cosine omega b minus theta 1 minus theta 2. Now, when r is bigger than root 2, remember, for displacement transmissibility, which was big X over big Y, actually everything went below 1, below the ratio 1. That doesn't happen here, okay? So unlike the displacement transmissibility, the force transmitted does not necessarily fall off, because if you go back to the previous slide, you see a graph of big X over ky, big X over y, sorry, big X over big Y. You see that they all went below the line big X over big Y equal to 1. That doesn't have, they all dropped. That doesn't happen here. Okay? But these formulas are important when it comes to designing suspension systems. Okay? So and you know, basically preventing unwanted and undesirable vibrations. These are extremely important. All right. Let's do an example. Okay, let's do an example here. We have a suspension system of a modeled car here displayed. The road is bumpy and it's going to be approximated as a sinusoid like that, with an amplitude peak-to-peak value of 0.02. Okay, now remember, this is not big Y, it's 2 times big Y. Okay, and there is a wavelength of the road which is 6 meter. Okay, now suppose I mean based on the information that's given, first of all, big Y is right here. You can see that is half of that. So 0.01 times sine omega bt. Suppose that the roads approximate with the sinusoid like this. The only thing is that we have to calculate what this omega b is. Some information is given here, okay? Some information is given in terms of, for example, the wavelength, and you will see the speed of the car also, the velocity of the car also has an effect on this omega b, okay? Now, we're going to find it, and what you want to know is what is the, determine the effect of speed on the amplitude of the displacement of the car chassis right here, okay? As well as we want to investigate the effect of the mass of the car, okay? So what you want to know is what is the effect of the mass of the car and the speed of the car on the overall problem. All right. Suppose that the stiffness of the spring and the damping coefficient based on some calculation in your vehicle dynamics class was represented by these numbers. Okay, let's start with the mass of 1,007 kilograms. Suppose the mass is known. Suppose the mass is known, and let's take a speed of, for example, in general V. In general V, we're given K, C, and M. We know that. And let's say that the speed of the car is V. In a few minutes, in a minute or so, we will actually select the value for V. But for now, let's assume it's V. Now, let me show you how to get the frequency right away. First of all, if the speed is V, okay, the time that it takes to go from this peak to this peak is 6 over V. 6 over V is 6 meter over V is going to give you the time that it takes from here to here, go from here to here. So that is the time period. The frequency in hertz is the flipped over version of that. So it's going to be V over 6 meters. So V over 6 meter is the frequency of essentially that motion, okay? The time period of it is 6 over V. V over 6 is the frequency of it, but in hertz. You multiply it by 2 pi, you're going to get in radians per second. And that is done in this line here, except that units have to be corrected. Remember, V over 6, we have to do it in kilometers, because if V is given in kilometers, I'm gonna turn everything into kilometers, okay? So V over 6 is going to give you the uh, uh, the frequency in hertz, okay? Frequency in hertz, except that we have to convert these hours into minutes, into seconds, and then we multiply by 2 pi, you get radians per second. So 0.2909 times V is the frequency of the oscillation. If V in radians per second, if V is given in kilometers per hour. Okay, if you give me the speed of the car in kilometers per hour, I multiply it by 2909 and I get the driving frequency in radians per second. Okay, all right. So suppose now it's 20 kilometers per hour. Suppose the car, if this is a car, yeah, is moving with a speed of 20 kilometers per hour. So the frequency omega b, just plug in 20 here, you get 5.818 rad per second. And then what we want to find is the big X. We have big Y, we want big X. All right. In order to find big X, remember big X depends on big Y, damping ratio zeta, and frequency ratio omega b over omega n. So I need omega n. So this is the mass of the car, this is the stiffness of the car, K over m, square root of K over m. Stiffness of the spring over the mass of the car, 19.93 rad per second. We can find R, which is omega b, we calculated up here, divided by omega n, that's 0.292. We have the value of damping coefficient. Out of this damping coefficient and K and M, we can find zeta. It's just the formula. There's the zeta. And now we go to our good old formula of big X in terms of big Y, or the displacement transmissibility right there. Big X over big Y is called displacement transmissibility. We have this formula for it. You know everything. And you get 0.011. So a road amplitude of 1 centimeter, 0.01, big Y being 0.01, means if the road amplitude was of variation of the road was 0.01 meters, which means 1 centimeter, the car chassis will move as 1.1 centimeter. Okay? Now, so we have solved it for this particular problem. If you gave me V, and if you gave me mass of the car, I could find big X. Okay? So let's go ahead and look at a table where it classifies several different velocities and two different cars, a big car and a small car, because we can do exactly the same calculation once the information is given to us. So we are looking at two cars. Car 1, the small one, its mass is 1007, the one that we just did. Okay? And we get almost 1.1. Remember, I didn't get 1.08. I got 1.1 because it was rounded off. Now, the big car has a mass of 1585 kilogram. Okay. And we haven't done it. Obviously, same calculation that we did for the first row of the small car can be done with all these other cases. So this is the column for the small car. That's the one that we just did, except that it was 1.1 rounded off. And a couple of things you notice that if you look at this, this is for the big car. Notice a couple of things. First of all, at higher speeds, 100 kilometers per hour or 150 kilometers per hour, The big car shows you a smaller cabin deflection or chassis deflection than the small car. These are the big car. This is the small car. These are the small car. Okay. So with higher speed, less vibration is experienced by the occupants of the larger car, because you can see that this is smaller than that and this is smaller than this. And that the suspension system, and this is the column for the big car, the suspension system parameters chosen, K and C, works better in general for the larger car, except at low speed. At low speeds, those suspension values that we have taken, yeah, they work, but not as good as for the higher speeds. Okay, let's do another example. Suppose we have a gigantic machine, rotating machine that is uh, basically turning due to imbalance, and there's a punch press next door, close by, which, because of the vibration of this gigantic rotating machine, the ground also makes it move. So it basically creates a ground motion or a base motion for this punch press. Let's say that the floor displaces according to this formula. So about a millimeter vibration of the ground with that frequency of the rotating machine, whatever it is. So this is the base excitation problem for the punch press. And what we want to do is how much force is transmitted to the punch press because of the motion of the ground to the punch press. How much force is transmitted to the machine, the punch press, when it is operating at resonance? Okay, so what do we know? I want to find the force transmitted, big Ft, to this punch press at R equal to 1 at resonance, which means when the omega b of the gigantic machine, rotating machine, matches the natural frequency of the punch press, assuming that these are all single degree of freedom systems. So what do we know? This is the data that's given to us. This is the mass of the punch press. This is the assumptions that we are making about the foundation on which this punch press sits on. Obviously, you create some isolation between the punch press and the ground, and you're told that the stiffness of that isolation is 4,000, 40,000. The damping ratio, the damping constant is 900, etc. And what we know is we want to find f of t. Now, what was the formula for f of t? It was like this. Let me remind you that there is this r squared hanging around here because we are using forces. Okay? So, do we know stuff? We know k. We know y. It's given as 0.1 centimeter. Of course, we have to use the proper unit. We know r. R is equal to 1 at resonance. Okay? And we know zeta. Just plug it in. At resonance, R is equal to 1. This thing, kind of simplifies to that. And I just rewrote this thing as it is. Square root of 2 zeta squared is 2 zeta. Just simple algebra, simple algebra. So there is the expression written for your convenience one more time. We know everything. The C was given to us. The foundation on which that punch press sits was designed for that. C critical is given by that. All the information that we have is here, 0.04. And now we're going to take this thing and stick it in there. And we are going to get make sure you use the proper unit. 0.1 setting, it is 0.001 to be consistent with everything. Just plug it in, and you're going to get your FT. This is the force transmitted from the ground to the punch press uh, due to the motion of the ground. The force transmitted to the punch press, that mass, gigantic mass that sits on top of, well, not gigantic, the punch press that sits on top of the foundation that we have. Okay, so this is the force that that punch press is going to experience because of what is rotating next door and creating that base motion. All right, now here's a summary of what we have done. This is taken from Inman's book. It's called Window 5.1. If this is a fixed ground here, force transmissibility for the base being fixed base. This is the displacement transmissibility due to the motion of the base. This is the force transmissibility due to the displacement of the base. Notice that the difference between these two, when you compare them, there is this r squared here, which is not there. And also here you have the value of f naught right there, you just put it in there, but there is non-dimensionalized by taking the stiffness of the spring and multiplied by the amplitude, amplitude of the base. All right, so the last item that we're going to discuss is rotating unbalance. We just set the stage for Thursday's lecture. Okay, rotating unbalance is a very common source of vibration. So it can be very detrimental to the health of the unit, and it's mainly coming from rotating machines, for example. It can be electric motors, or it can be combustion rotating component due to the internal combustion engine, etc. Now, a small irregularity in the geometry or the mass distribution of these rotating pieces can cause severe vibrations. Okay. So let me, for the sake of illustration, I'll show you something on the right-hand side. So we have a rotating component here, and it is within a machine, and the box is, because of the rotating unbalance, keeps going up and down, and of course the sideways. But the main concern here is the vertical motion, or the degree of freedom where this thing moves up and down. Now, generally speaking, these machines are always mounted on foundation that's designed for them, such as rubber cushions, and which can be assumed to be a spring and a damper in parallel. Now, of course, sideways vibration is also important, but for us, it's only the vertical, as shown here in the x direction, that's of interest. Now, let me assume that the mass of the rotating component is m naught, and let's pretend that the mass center of this rotating component is the distance e from the center of rotation. So here it's shown to you as a mass m naught, which is a distance e away from the center of rotation. So, for example, if this was actually a complicated, object, such as a set of fan blades, etc., rotating, or a turbine, etc. So, what you do is, obviously, you know where the center of rotation is, where the axis of the shaft comes into, makes it rotate. But you can calculate the mass of this object, whatever it is, whatever is rotating, the mass of it, calculate it, and find out where the mass center is. So pretend it is a lumped mass at that mass center, which is a distance away by E from the center of rotation. So the center of mass, the distance between the center of mass, center of rotation, we called it E, standing for eccentricity, and the mass of the rotating component, whatever it is, you put it at the mass center. So it's as if this whole thing becomes as if a mass attached with a link to the center of rotation is turning around at a speed, for example, omega r. Okay, rotating. The R stands for rotating. Okay. So what I would like to do and what we will do in the next slide, get the mother of all equation for the displacement, vertical displacement of the machine. The machine is this big block that you see here, which is going up and down. Now, of course, this rotating component is also sitting in it. But when it comes to getting the equation of motion, the mother of all equation, we take the mass that is rotating and replace it with the effect that it puts at the center of rotation. So basically, we can eliminate the m naught to some extent from when it comes to the getting the equation of motion. So let's go ahead here. Here's the situation. M naught is the unbalanced mass. In other words, that's rotating component. And M, the thing that is the mass of the machine. The mass of the machine is actually m minus, let me put it this way. The mass of the machine, of course, is m plus m naught. I understand that. But the mass of this block, is going to be m machine minus the rotating component. This is the mass of the block. Okay? And we said how to visualize this thing. So this rotating component can be thought of as a lumped mass here, a distance e away, which is turning. Okay, so our x is pointing up. You can see that. Therefore, the position of this rotating mass is simply x, because the whole box is going up, plus the fact that it's rotating xr of t. Okay, so at any instance, this block is at location x, but the mass itself, the rotating mass itself, or the unbalanced mass itself, is at location x plus xr. Okay? Okay? Good. Now, we can actually find out what this, where the position of the mass is, but the vertical displacement of it is simply xr of t, which is going to be e sine of omega t, as you will see. All right, let's look at the diagram on the left. Okay, the diagram on the left. Look at what I've done. I have replaced the rotating component with its force on the box, Fr, okay? And because these are internal, when it comes to the mass, rotating mass itself, Fr is pointed down, okay? So what I'm assuming here is the force on the box, which is making it go up, is Fr, and therefore the force on the mass at that pin location is Fr pointing down, okay? And when you look at the free body diagram of the mass, is mass of the rotating component times the vertical acceleration of it, which is second derivative of x plus second derivative of xr, equal to the external force that's acting on it, which we assume to be minus Fr. Now, when you look at the box itself, is mass is m minus m naught right there, okay? Because we have removed the rotating component from it. And what are the forces that are acting on it? There is, of course, Fr, which we assume is pointing up, and there is spring force and the damper force that are opposing that motion. So it's going to be minus kx minus cx dot. This is the free body diagram. This is the equation of motion for the vertical displacement of the rotating component. This is the uh, equation of motion for the displacement, vertical displacement of this box. Now we can add these two, can't we? This is true and this is true. We add them, FR goes away. And also M naught times X double dot goes away. Okay? Goes away. So this is what we are left with. Now the question is, what are we going to do with this XR? Okay, first of all, we know what XR is. The position of this mass M naught as a function of time is right here. So vertical position is this in this right triangle that I have here is the eccentricity times the sine of that angle right there. See that? This is the vertical position. This is the vertical position, which is your XR. Okay? And in this right triangle here, this XR is simply E sine of omega t. And I need in my equation right here X double dot of R. So you differentiate it twice, you get a minus sign. Take that and stick it in that equation, get rid of XR basically, and you get the mother of all equations for a rotating unbalanced machine. Right there. Notice that we know how to solve problems like this. So we have mx double dot plus cx dot plus kx equal to a force, and that force is harmonic. The magnitude of the force, remember we called something F naught? That was the thing that's multiplied by sine. Essentially, this is F naught. So everything that we have done for a harmonically loaded mass spring damper system is applicable. And we're going to do that in detail on Thursday. Good luck.